Hello, the subject of this presentation is live loads. In this lecture, we'll focus on live loads for building type structures, and we'll leave the discussion of bridge live loads for another time. Let's get started. Like dead loads, live loads are covered in Chapter 3 of both Tally and Finella. In the Tally textbook, you could review Section 3.1 again, and then Sections 3.3 and 3.4 to cover live loads and roof live loads. And then again, Section 3.5 covers gravity loads on multiple story columns. And then there are some other sections in Tally that cover different types of loads that would also be considered live loads, like helicopter pads and railings and things of that nature. I'm not intending to focus on that in this course. In the Finella text, section 3.3 is where you want to look, but there's also some additional material in that chapter that covers things like helicopter landing pads and things of that nature. So let's start off again in the International Building Code. Section 1607 defines what live loads are, and it says that live loads are loads that are produced by the use and occupancy of the building or other structure that does not include construction or environmental loads such as wind, snow, rain, earthquake, flood, or dead load. The definition that's in Chapter 4 of ASCE 7 is nearly identical to the one that's in the International Building Code. Live loads are transient in nature and can vary over the life of the structure. That makes them fundamentally different than dead loads. Dead loads are permanent loads and they're assumed to always be present on the structure, but live loads are not. They're different. Studies have shown that building live loads consists of both a sustained portion and a variable portion. The sustained portion is basically there most of the time and consists of things like desks and chairs and tables and equipment and maybe filing cabinets that are in the room. The variable portion is typically the occupants or the tenants that would enter or leave. So take a classroom, for example. You have a number of desks and tables, probably some computers and chalkboards and things like that. That would be the sustained portion. The load imposed by the students and the teachers entering and leaving would be the variable portion. But it's important to note, too, that things can change over the life of the structure. So one thing to bear in mind is you might want to design not just for the load that you think is going to be in the structure right after it's opened, but maybe give some thought to designing the structure for what it might possibly be used for in the future. And also bear in mind that live loads can include high magnitude events, things like if you have a renovation or remodeling of the structure during its life, then you might see a load in a structure that is higher than what you would consider for your day-to-day use, but would also be considered part of the live load. Okay, live loads are generally modeled as an area load, pounds per square foot, but in a lot of cases we also consider concentrated loads as part of the live loading. Okay, floors, roofs, and other similar surfaces shall be designed to support a uniformly distributed live load or a concentrated load that are provided in Table 4.3-1 of ASCE 7-16, and you take the results of whichever one produces the greater load effect. This is an example of that table. This table, like the table of dead loads, is several pages long, and I'll post an excerpt of that in the PDF version of this presentation. But you can see some of the loads here. Office use would be a uniform load of 50 pounds per square foot or a concentrated load of 2,000 pounds. There's a lot of different examples here. Okay, concentrated loads, when you design for them, shall be distributed over an area that's 2.5 feet square and shall be located so as to produce the maximum load effect in the member under consideration. Okay, in selecting the occupancy or use for a building, you should give consideration to the possibility that changes in the structure might lead to heavier loads than originally contemplated. We mentioned that just a couple of slides ago. Okay, there's also a discussion of partitions, and partitions may or may not be considered to be a dead load or a live load. So if you go back into older specifications, I'm not terribly familiar myself, but I think if you go back to like the Uniform Building Code, that you can see examples where partition loads were considered to be dead loads at one point. But when we talk about partition loads that are live loads, then we're thinking about the type of partition wall that can be moved. So we're not talking about a load-bearing wall that has to be there, but we're talking about just a wall that separates the bathroom from the office space, or maybe a wall that separates the supervisor's office from the general workers. So this is generally just gypsum board on metal studs or wooden studs, and it can be removed at any point and moved around. And the basis for the partition load is shown in this slide, where basically the assumption is that you have a 10-foot high wall with either metal or wooden studs, half-inch gypsum on both sides. That would give you a weight of 80 pounds per linear foot for the wall. Now, if the partitions are spaced on the floor area on a 10-foot by 10-foot grid, then that would basically give you 16 pounds per square foot on the floor, based on the wall loading of 80 pounds per linear foot. And then if you take a design value of 15 pounds per square foot, that's deemed to be reasonable based on 16 to 15, nice round number. But if you have different types of walls, you would want to make sure you consider that in your design as well. Maybe if you have a CMU wall or concrete block wall, that would probably give you a higher partition load than the 15 pounds per square foot. Okay, there are loads given in the International Building Code as well, section 1607. They are largely consistent with what you'll see in ASCE 7, chapter 4. This is a snippet out of the Architect Studio Companion. This is an interesting textbook. It's meant for architects, but there's a lot of good information in there for engineers as well that can be used for preliminary design. What I like about this particular image is that it gives a visual indication of the types of loads that you're going to be designing for. So for an assembly area, you design from anywhere between 60 to 100 pounds per square foot. For a garage, the most heavy loading you would design there for is about 250 pounds per square foot. Manufacturing facilities, somewhere between, say, 125 to 250 pounds per square foot. And then continuing that image on this slide, you can see office buildings are designed from anywhere from 50 to 100 pounds per square foot, and then storage areas up to about 250 pounds per square foot. So what does a live load actually look like? Well, this is an image taken out of a textbook on the reliability of structures by Nowak and Collins. And they took a 6-foot square area and they loaded it with enough people to give the equivalent of about 50 pounds per square foot of load. So you can see that's kind of like what you would typically see in an elevator, perhaps, on a normal day. If you add some more people to it, you can see that that's about 100 pounds per square foot. And then taking it a little bit further even, you can see that if you really cram that space full of people, then you get to about 150 pounds per square foot. So you might remember from our discussion of load combinations that when you get to a live load that's 100 pounds per square foot or greater than 100 pounds per square foot, there's some changes in the way that that live load is considered. And that difference is basically based on the idea that areas of public assembly might actually see people that are crammed into a space as tightly as could be. So think of a rock concert or think of a Bengals game. Well, all right, maybe not a Bengals game because Bengals aren't really that great, but think of, say, a Steelers football game where people are trying to get in and see the action and things of that nature. So just some visual examples of what a live load is like. Here are some other examples of various live loads. If you have filing cabinets with spaced in an office or a room with 36-inch aisle widths, then that corresponds to about 150 pounds per square foot. If you have library stack rooms, then that corresponds to 150 pounds per square foot as well, assuming that you have double-faced library stacks with 12-inch deep shelves, no higher than 90 inches, and aisles that are 36 feet wide as well. Mobile shelving in libraries, however, can give you a much higher loading. It might actually be higher than 300 pounds per square foot. And then if you consider the storage of medical files, X-ray film, for example, it might exceed 200 pounds per square foot because the film itself is heavier than paper would be. In many cases, we're permitted to reduce the live load that we design our members for, based mostly on the use of the structure and on how much tributary area a member supports. So consider, for example, a member that supports a relatively small tributary area, maybe something in the order of 100 square feet or something of that nature. The possibility of getting a full live load in that area is quite reasonable. So in that case, we wouldn't be able to design for reduced live load. But consider a column that supports several levels of flooring and might support a tributary area that is in the thousands of square feet. The odds of all of that tributary area being loaded to its full design load is much lower than the first case. So in that case, where the tributary area is higher, we're permitted to design for a reduced live load. Okay, the reduction looks like this, where you have L0, the unreduced live load, and then you have L, the reduced live load. And this equation is based on the tributary area A sub T and a factor K sub LL. Okay, K sub LL is the live load element factor. And when you multiply that by A sub T, you basically get the influence area for a particular member. Remember that discussion from a couple of lectures ago. So the product of K sub LL and A sub T is basically the influence area for a member, and you're allowed to calculate that directly instead of using K sub LL. Now there are minimum values for the reduced live load. The reduced live load can't be any lower than 50% of the unreduced live load for members supporting one floor, or 40% of the unreduced live load for members supporting two or more floors. So there is a lower bound to that. This is a table that represents K sub LL. It's basically the ratio of the influence area to the tributary area for any given member. So it's based on whether you're looking at an interior column, an edge column, a corner column, or some other type of member. Note the footnote here, though, in lieu of the preceding values, K sub LL is permitted to be calculated. So you could take K sub LL directly as the ratio of the influence area to the tributary area for a member. And then this is an image out of the Finella textbook that gives a graphical representation of our live loads that we're designing for. So the reduction multiplier is on the vertical axis. So when you have a value of 1, that means that you're providing no reduction in the live load at all. When you have a value of 0.5, that means you're reducing the live load by 50%. So what this does is it gives a good illustration of how the live load reduction varies over the influence area of the member. So as the influence area of the member gets larger, then the amount of reduction that you're allowed to take for a member gets larger as well, or the live load you design for is a smaller portion of the unreduced live load. Okay, the live load reduction is also found in the International Building Code. In fact, the default equation is identical to the one that's found in the ASCE 7 standard as well. Now, I should mention that this equation only works in imperial units. This works if you're using units of square feet, and there is a separate equation if you're using SI units. There's a second equation that's provided in the International Building Code, however, and this is, I think, based on a throwback to the older building codes. I'm not positive of that, though. I probably shouldn't have said it, but I'm going to leave it in there anyways. I'm not going to emphasize this much in my work, but there are some problems in the Finella textbook where they use the alternate live load reduction. There are some exceptions, however, where this equation applies, and in fact, where live load reduction in general applies. When you're looking at areas of public assembly, then you wouldn't really want to provide a reduction in the live load, because even if you have a large influence area or tributary area for your member, it is quite conceivable for that full area to be loaded to its maximum or full design load. And then that's typically in cases where you see live loads greater than 100 pounds per square foot, for example. Garages for passenger vehicles is another example. And then the fourth one, I think, is specific to the alternate form of the live load reduction in the International Building Code. When we apply live loading to a structure, we need to think about how the structure reacts or how the structure carries load when we choose our application. So consider this multiple span beam. We have 1, 2, 3, 6 spans on the structure, and this is an influence line shown for span CD, positive moment in span CD. So if we were going to apply our live load to this continuous beam in order to maximize the moment in span CD, we would want to apply that live load like is shown here at the bottom of the slide. We would want to apply live load over span AB, span CD, and span EF. If we put live load in span BC, span DE, or span FG, that would actually reduce the felt moment at the point of interest. So we wouldn't put the live load in those regions, thus the transient nature of live loads. If we look at the negative moment over the support at D now instead, then the application of the live load varies again. In order to maximize the negative moment over span D, we would put the live load as is shown here. Now, this is very important when we consider the design of concrete structures. In the design of a concrete structure where everything is framed continuous, in other words, there is a moment connection between each beam and each column, then we have to be cognizant of the way the building carries the load when we apply the live load. So consider this. This would be an influence line for positive moment in the middle of one of these bays. If we were going to apply the live load to this structure such as to maximize the positive moment, then we would only load every other bay in a pattern that looks like this. Now, this is referred to by structural engineers as a checkerboard loading, and it's important to keep this in mind when we apply our live loads, because this maximizes the live load effect for positive moment in one of the members. Now, again, when we look at a steel structures are typically not framed continuous. Typically, you have a web connection between most beams and columns. And if you have that web connection, then you model the beams as pinned. And if you were to sketch the influence line for a beam in a simply framed structure, then the load in the next bay doesn't influence the moment on the beam that you're looking at in the current bay. There are continuous frames in steel buildings. However, if you look at a moment resisting frame that's part of a lateral force resisting system, then you would have a similar situation to what's depicted here. It's certainly more commonly encountered, though, for concrete structures than it is for steel structures. All right, we'll shift our attention now to roof live loading instead of just general live loads. And we'll go first to the International Building Code. And the International Building Code defines a roof live load as a live load that's imposed during maintenance work by workers, equipment, and materials. A load that's imposed during the life of the structure by movable objects such as planters or other decorative appurtenances, or the use and the occupancy of the roof. Now, the definition in ASCE 7 is very similar, with one exception. It does say that occupancy-related live load on the roof, such as assembly areas and decks and things of that nature, is considered to be a live load rather than a roof live load. And that's a subtle difference, but it's important because when you remember the load combinations, there are different load factors applied to the live load than there are to the roof live load. Okay, and I'll go back to this image again of the roof of Zimmer Auditorium as a case where, say, the students walking across this roof, for instance, would be considered a live load per ASCE 7, and then all of the greenery and the landscaping elements would be considered part of the dead load. You're allowed to reduce the live loads on a roof like you are the live loads on a floor. However, the equations that we use for reducing roof live loads are a bit different than those that we use for reducing floor live loads. Those are presented here, and they'll be illustrated in some example problems. Okay, that brings us to the end of this lecture. Hopefully now you have an idea of how live loads are determined and how they're applied to structures. Thanks.